So today I'm going to talk about electromagnetic shielding. Now this is of particular interest to people who are concerned about electromagnetic pulse attacks, or maybe EMI, where you're worried about emissions that might be affecting you. And people wonder, well, how do I effectively shield against that electromagnetic energy, right? That's what we're going to talk about today. And I know you see a board filled with a bunch of stuff, equations and graphs and so forth, and it might look very confusing right now. But what we're going to do is walk through each piece of it, and by the end of it, there'll be some very useful takeaways that you can remember about what works and why in terms of electromagnetic shielding. All right, so let's start with just some definitions, okay? So the first thing is we have some kind of source of the electromagnetic energy, or it generates some kind of waves. So think of that as some kind of antenna. And that source is some distance away, and that will be important. And it also has some source characteristics, like is it a rod that's just sort of radiating, like the old car antennas on your car? Or is it some kind of a loop that just has a current flowing in it that's also radiating? Those are very different kind of waves that come out. So there's some kind of a source that's generating a wave, and it has an electric field, a magnetic field, and a frequency, all right? When that wave comes and strikes a conductive barrier, and that's what this region here is, some of the energy reflects off, all right? That's good. You're trying to keep the energy from getting through it. And some of the energy passes into the metal but gets absorbed along the way with just a little bit of it getting through, all right? So there's two aspects to what the conductive barrier does. It reflects energy off, and it also absorbs energy that comes into it, all right? Now, it's not perfect, so some does get through. And then there's some complex interactions inside the metal where you get internal reflections. When the wave hits the barrier on the other side, it gets reflected, and this happens over and over. And so normally we're going to neglect that, but just be aware that happens. The metal's not really just absorbing and letting through. It's also having some actions that occur inside of it. Now, we can talk about something called the wave impedance, and it really just has to do with the type of source that generated the wave, right? And we're going to talk about that in a minute with one of these other figures. And then there's an impedance also of the conductor, all right? And that impedance of the conductor is really just a function of its specifics. So if it's aluminum or copper or steel, each conductor has a permeativity, a permeability, and a conductivity. And those things roll into how it's going to act in terms of its impedance, all right? And it's the mismatch between these impedances that really leads to this shielding, all right? And so we could calculate those things, and you can run them through simulators and determine how well a particular conductor acts as a shield, okay? So maybe when you calculate the shielding effectiveness, and again, that's really just a measure of what percentage is on the other side of the barrier from what came in, right? You want as small a percentage as possible, and you convert that to something called a decibel, which is just a logarithmic ratio, and you'll get some kind of shielding effectiveness. The higher, the better, okay? So let's say you had 140 dB, it might be made up of three components. It would have a reflected term, that's again what's due to the reflection occurring, an absorption term, in other words, how much got absorbed as it went through the metal, and then there'd be this loss mechanism that occurs because of these complex reflections inside. Now again, normally, as I said, this is pretty small, and so we typically ignore that, and we just look at reflection and absorption, all right? And that's what we're going to do today. We'll talk about when one matters, when the other matters, and that's kind of the meat of the whole thing, right? When does reflection dominate? When does absorption dominate? Why don't they work well sometimes, okay? So this is the general idea. Incident wave comes in, some gets reflected, some gets absorbed, some gets through to the other side, but we want that as small as possible. All right, let's move to the next figure here. This is where we're going to talk about the wave impedance. Again, that source that's generating the electromagnetic wave could be many different types of things, but we like to sort of dumb it down into two sort of extreme cases. One might be like a monopole, again, just like a metal rod that's just radiating electromagnetic energy, and the other might be a loop. So you think about just a loop of wire that has current flowing in it, and that's going to radiate some kind of electromagnetic energy. Now, if you have this monopole style antenna, you're going to have a very high electric field when you're close to it. Okay, so this is the distance from the antenna, and this is the wave impedance. And so you're going to, and this axis, this wave impedance means the E over H, the electric field over the magnetic field, the ratio of those two. So you're going to have very high electric field when you're close to a monopole antenna, all right? And you're going to have very low electric field when you're close to a loop antenna, all right? So essentially the ratio is going to be very small. You'll have much more magnetic field than you would electric field for a loop antenna, and you'll have much more electric field than you have magnetic field when you're close to a monopole antenna. That's really important to know. So I'll say it one more time. If you're close to a loop antenna, you're going to have a lot of magnetic field when compared to the electric field. When you're close to a monopole style antenna, you're going to have a lot of electric field compared to the magnetic field. All right, that's what this is trying to tell you here. Now, what's interesting is as you move further away from the antenna, they come together. All right, they come together, and eventually they come to the same value. All right, and in free space, that's a fixed number. It's 377. So the electric field to magnetic field ratio is 377 when you get far enough away from either of these two types of antennas, either extreme, which is really fascinating. All right, so it means if you get far enough away, it doesn't matter what kind of antenna you had. But when you're up close to the antenna, it makes a big difference in terms of this wave impedance. All right, and the wave impedance is going to be very important in determining how this shielding effectiveness works out. All right, so that's what this chart is saying here. Now, where do we put the line that says, hey, they've come together and this ratio is 377 versus they're very, very different. One dominates or the other dominates. And we usually just to simplify it, and there's a little more to it, but I'm going to simplify it. We'll just put a line at essentially the wavelength divided by 2 pi, all right? And the wavelength of the incident wave divided by 2 pi, we'll let that be a number. And if we're closer than that number, and this is measured in meters, we're going to say it's in the near field, and that's where these effects happen. The antenna type really matters. You end up with a lot of magnetic field or a lot of electric field. And if you're further away than that, you're in something we'll call the far field, right? And if you're in the far field, it really doesn't matter what type of antenna source it was because you have a fixed E to H ratio, okay? That 377. And you can calculate that. It's just the dividing between the permeability and the permittivity, and you get the 377, okay? All right, so once you're in this, the ratio stays the same. Once you're in the far field, the ratio stays the same. And the electric field and the magnetic field both roll off as 1 over R, all right? So as R increases, the E and H both decrease. So if you double R, the E gets down by a half and H gets down by a half. It's just 1 over R, all right? Now notice that's not what happens here. E and H change very differently and much faster. So they're not 1 over R. They might be 1 over R squared or 1 over R cubed when you're in these regions here. They change much more rapidly with distance than when you're in the far field. Okay, and that's part of the theory behind propagating for radios and communication systems and stuff like this is this 1 over R understanding. Okay, so what was the point of all this? It was just to say, hey, monopole and loop antennas behave differently in the near field, right? They have very different wave impedances. But in the far field, essentially, they look the same. They're just an electromagnetic wave now with a fixed ratio, right, with a fixed wave impedance. Okay, so that's what that table says. Now, what did all that tell us? Well, it set the stage for where we're going to go looking at shielding effectiveness. All right, so let's take a look at a plot of absorption and reflection. Notice we're going versus frequency. This is the absorption in dB and the reflection in dB. Let's see what it shows us. The absorption increases with frequency. The higher the frequency, the more absorption you get. Now I just put just a number, maybe 50 dB, and then there could be 100 dB and so forth. So as you increase the frequency, you get more and more absorption. It doesn't matter whether you have which type of antenna, both high and low wave impedance sources behave the same. You're going to get more and more absorption as you go to high frequencies. Great. All right, so, and that just says that, hey, a metal is going to absorb incident electromagnetic energy regardless of its source as you get higher and higher in frequency. Okay, now notice at low frequency, you get very little absorption, right? And that's important to know. Now let's look at reflection. Again, that's the energy bouncing off, right? There are two different curves, okay? And so it depends now on the type of antenna that you had that was generating it, right? And how close you were to it. So again, do we have a low or a high wave impedance? Are we in one of these regions here? And if you're in the near field and you have a high, so in general, if you have a high wave impedance, all right, so you have a high wave impedance, that might mean that what? We're in this region right here. We have a very high wave impedance, so we have a monopole and we're up close to it. You would follow this curve here, okay, the blue curve. And if you have a low wave impedance, so maybe you're on this red curve here, all right, you're down here, you've got very low wave impedance, you're going to follow this curve here, okay? So what does it tell me? It tells me that you get really good reflection from this electric field dominated emission, right? You got really high values of reflection, that gets reflected off really easy. But this magnetically dominated emission really doesn't get much reflection. It manages to not get reflected off the metal. All right, so that's how it's showing you the reflection is really dependent on the type of the source, all right, the wave impedance, which is dependent on the source and the distance. Now notice if I get out far enough, I'm not really in either one of these. I'm in the middle somewhere, all right? I'm not really a high wave impedance or a low wave impedance. I'm in between the two. But in general, reflection works pretty well when you get up to higher frequencies, and we'll see that in just a minute. Okay, so that's what this is saying, is absorption is really not dependent on the wave impedance. It's just frequency dependent, but the reflection is very dependent. All right, let's go on here. All right, so let's take a look at a combination of the two, because remember, both of these are occurring, right? We're getting reflection and absorption. So let's put them together. Let's add them together. And there's a few things to know, but let's start with just the picture here. So there's my absorption curve, this black line, and there's maybe the reflection curve for a high source impedance, right? So that's this blue one that was here. So we just combined those two, and now let's see what happens. Well, I'm going to just follow sort of the sum of those two. I'm going to add those two curves together, and you're going to end up with something that looks like this blue curve, all right? So again, remember, we were on this curve here, which is for high wave impedances, which means this electric field dominated source. It says, hey, I get really, really good combined shielding at low frequencies. It kind of dips down in the middle frequency range, and then it goes back up at the high frequencies. So you get excellent shielding at all frequencies when you have a high wave impedance like a monopole type emission here. So that's great. So for a high source impedance, you get excellent shielding at all frequencies. There's no real concerns. You can get very, very large shielding values. And in fact, it really doesn't get dominated at all by the conductor anymore. It's by the flaws in your shielding, right? Maybe you have gaps or seams or holes, and that ends up dominating the shielding effectiveness, not the fundamental limiting aspects of your absorption and your reflection. Because these numbers are very, very high, maybe 150 dB and up. And it's very difficult to actually achieve 150 dB in real practice because of those imperfections of your shield, you know, the lid, the door, whatever kind of things you had to add to your shielded enclosure. All right, so this is good news. It says, hey, if I have a high source impedance source, I can use shielding to block it very easily. I can get a lot of shielding, as long as I'm careful with how I make my box. Now, let's take a look at a low source impedance source. What is that again? That's a loop antenna, all right? So loop antenna generates some wave. Notice what happens. For low frequencies, I took this red curve and this curve now and combined them. I end up with this combined curve here, this blue one. Notice what happens. At very low frequencies, I have terrible absorption and terrible reflection. So I really don't get hardly any shielding at all, which is not good news, right? So poor shielding against magnetic fields at low frequencies is what we're saying. Again, that loop antenna generated magnetically dominated field when you're in the near field. So it does show that at high frequencies, you can block that incident electromagnetic wave, but not so well at low frequencies. And that's really where the rub comes in. So when you have a low impedance source like a loop antenna, and you're in the near field, right? That means you're here. So you've got a lot of magnetic field compared to the electric field. You just don't get, the shielding doesn't work very well at it for low frequency emissions. And that's why it's so hard to block things like 60 hertz, that we use for our power, that's circulating around these wires in these big loops in our home and other places, and you generate these magnetic fields off of them. It's difficult to shield against those very low frequencies that are generated by magnetic loops, okay? Loop antennas. All right, so that's what that says. Now, how do you handle it then? Do you just give up and you can't shield against these type of fields? Well, not exactly. To shield against low frequency magnetic fields, you have to use special materials. You can't just use copper or aluminum or any other of those metals that you normally use to shield, you think I'm going to shield against Wi-Fi or something like that. To shield against very low frequency magnetic fields, you need special materials. And those special materials have very high permeability, all right, very high permeability. And they form what's called a low reluctance path. So if you think about like a magnet, and let's just think of that as a time varying magnet where its magnetic field's changing. The magnetic fields, of course, go out one side and come in the other, one end go in the other. But if I put a barrier of this very high permeability material, it will steer the magnetic field lines through it and then let them route back around. Rather than let them come through, it will sort of capture those magnetic field lines and collect them and let it close its loop the way it's supposed to. And that means on this other side, you don't see the magnetic field or not as much of a magnetic field as you would have, all right? But you have to have these high permeability materials, which are typically very expensive to use in shielding. So you'll see terms like permalloy, or mu metal is often, people talk about mu metal. But even nickel works pretty well. And so you get this relative permeability versus frequency, and they're very high at these low frequencies, and that's what you want, is very high permeability for this to work for you, okay? So this is really the only way you shield versus these magnetically dominated emissions, right, where you're in the near field of these loop antennas using these high permeability materials. All right, so we're about at the end here. Let's do our takeaways and see what matters here. The shield material, all right, how important is the shield material? Well, that kind of depends. All conductors are good for electromagnetic fields in the far field. When I'm out here in the far field, everything kind of looks the same and I can block it pretty well with any kind of metal. All metals are really good conductors, so copper, aluminum, whatever. Those all work well if the field is in the far field. So what about an EMP? Well, an EMP is hundreds of miles away. By the time the energy reaches whatever you're trying to protect, you're in the far field. You're certainly far enough away you're in the far field. And so it would be able to be protected against quite well with any kind of conductive material, all right? However, if you're trying to block 60 hertz from, a big antenna in your wall, big loop antenna, that's not going to be blocked very well by all conductors, all right? If you're in the near field, that down in this region here, it works, any kind of metal would work fine as long as it's, an E field dominated, an electric field dominated antenna, but not so much if it's a magnetic field dominated material. And that's what this is saying here. Low frequency magnetic fields in the near field require special materials. That's these special high permeability materials. All right, so that's about the material itself. So number 2, well, how do you make a shield really good? I didn't talk about any here, but what I mentioned was that in many cases, you have really great potential shielding that you can implement. What ends up compromising you are the holes and the slots and the various imperfections in your shield. And so you can calculate the shielding effectiveness as simply 20 log of the wavelength over 2L, where L is the maximum distance across the hole. All right, so maybe corner to corner if you had a slot like this. And you can see what kind of shielding effectiveness you can get with these type of slots or imperfections, all right? The short answer is if you have no imperfections, no holes at all, you can end up with an incredibly high shielding value. But as soon as you start adding in imperfections, you want these slots to not be very long and not be narrow. It's much better to have a round hole in your shield than it is a long, narrow slot because the distance from corner to corner is much bigger than the diameter of a circle. All right, so you want to minimize the hole dimensions, any kind of imperfections in your shield. Next, you want to properly handle any penetrations to the shielded enclosure. So maybe you need to bring signals in or power in or something like that, and that happens many times for shielded enclosures. So ideally, you don't want to have any penetrations, but if you have to have them, you want to pass the signals through filters, so the filters would prevent any energy that's on those wires from getting into the box. Wave guides, if you're having to pass, let's say, fluids or air into the box, you can use special wave guides, which are just long tubes that are specially calculated in length and diameter that will not let the incident energy come through the tube. It just kind of gets attenuated as it tries to go through the tube. And you can use any kind of ferrites or shielding or anything like that on the penetrations as well. All right, so you have to handle the penetrations properly. That's the short answer of it. Or you can really compromise your shield and all of the work was for nothing if you end up not paying attention to penetration. Now, I didn't talk about grounding. And grounding I know is a big topic of do you ground the Faraday cage, do you not ground the Faraday cage? And none of this had to do with grounding. And grounding doesn't really play a role in these basic calculations, but it does play a role in how well things really work, all right? The short answer is this. If you're in the near field, so you're down in here, you're in the near field, it's very important that the shield be grounded, all right? It's very important if you're close to the antenna, that type of electromagnetic energy benefits greatly from being grounded, okay? So, and that good example of that is like wrapping around cables where you have a shield around a cable. It's very important that that shield be grounded. So near field, if you're in the near field, very important, ground your shield. If you're in the far field, it's much less important. I've done a video or two on this. So like for an EMP, I often say, it doesn't matter much if you ground your shield. And it doesn't. In reality, it doesn't. You can measure the energy is about the same either way. It's not to say there's not some benefits of grounding. Sometimes it's important to ground for safety and other reasons. But the benefits are much more limited when you're in the far field, when you're out here far away from the source, okay? So it may help prevent some re-radiating where energy gets on the shield and then radiates around a little bit. But in general, it's much less important, right? Which is why I say that. So that was sort of the fourth takeaway here. If you're in the near field, it is important that you properly ground the shield. Otherwise, it's not quite as important. All right, so a lot of stuff, pretty quick here. Again, talking about the reflections and absorptions on some kind of conductive barrier, how they vary with frequency, right? And how they also vary with what type of antenna it is. The net combined effects, the short answer is for high source impedances, you get great shielding all the time versus low source impedances. If you're at low frequencies, you get terrible shielding. So you have to go to this high permeability materials. And finally, sort of some takeaways to how to get it all to work. So I hope this was helpful. I tried to summarize it in a way without too much mathematical work. But I hope maybe it gave you a feel for when people talk about whether shielding is going to work or not work. Maybe you have sort of a reference now of what they're talking about in terms of the type of antenna and how far away you are, whether you're in the far field or the near field, reflection and absorption, and how they kind of work together to give you a combined shielding. All right? Anyway, I hope this was helpful. If you have any questions, feel free to post them. Keep an eye out for my next video.